So number 17, our function is 2x e to the x. The graph of f is concave down when. So concavity comes from the second derivative function. So we know we have to work our way down to the second derivative function. And let's see what it takes for us to get to f prime. So our function is 2x e to the x. And if I want to find the derivative, I have to go through the product rule. So I can treat 2x like my f function, treat e to the x as my g function, and I go through the product rule here. So f prime times g plus f g prime. The derivative for e to the x is e to the x times 1, and we clean that up to be 2e to the x plus 2x e to the x. So that takes us halfway there. We still have to find another derivative down to get to f double prime. So 2e to the x, we can just apply the rule e to the u times u prime, but 2x e to the x, this is going to require another set of product rule to find our derivative. So the derivative for 2e to the x is just going to be 2e to the x times 1, and then here's my f and there's my g. So f prime g plus f g prime. 2x becomes 2, e to the x stays, back to the f function, which is 2x, and then the derivative for e to the x is e to the x times 1. Clean all this up, we get 2e to the x plus 2e to the x. Combine those like terms, we get 4e to the x plus 2x e to the x. Now that we have our second derivative function, we know that we're going to be determining when the graph is concave down, so we're going to have to go through our concavity test. So let's find our critical points by setting f double prime equal to 0. Factor out the GCF. Set both portions equal to 0. If I set 2e to the x equal to 0, there's no critical points there, so I can ignore that. If I set 2 plus x equal to 0, I get x equals negative 2, so I do have one critical value that I can put onto my second derivative sign line. Now I'm going to choose values on either side of my critical point, so negative 3. If I plug negative 3 into my second derivative function, I'm going to get a negative value because 2e to any power is just going to be a positive value. 2 minus 3 is negative, so I know in this interval, concave down. If I plug 0 into this 0, that represents this portion of the sign line, into the second derivative function, I get 2 plus 0, which is 2. That's positive, so I have concave down, followed by concave up. So there's a point of inflection, but it's only asking for concave down, so we can say graph is concave down from negative infinity to negative 2, or less than negative 2. Number 18, we have the derivative g prime. It's continuous and has exactly 2 zeros. So remember, g prime represents the slope of the original graph. Selected values of g prime are given. If the domain is a set of all real numbers, then g is decreasing on which of the following intervals. So when g prime is 0, that means these are places where slope is 0. All right, slope is 0. And these g prime values represents whether the graph is rising, or as these negative values indicate, where the slope is negative or where the graph of g is falling. So we want to know when g is decreasing. So decreasing is going to be between negative 2 and 2, because these have the slope values that indicate negative slope. Okay, so answer choice A. Number 19. A curve has slope 2x plus 3. That's just a confusing way of saying f prime is equal to 2x plus 3. So 2x plus 3 represents the slope pattern of a particular function. So that's just basically saying f prime of x equals 2x plus 3. Which of the following is an equation for this curve? So we want to find f of x. So we have to find the antiderivative. So we're going to find the antiderivative to move our way from f prime up to f of x. Through that indefinite integral process, we're going to have a plus c that shows up. So we're going to solve for c using the order pair that's provided, and then after that, we can write our specific equation for our function. So we start off with f prime. We're going to take the antiderivative of 2x plus 3. That will move this 2x plus 3, this derivative, up a level to a function level. So the antiderivative, we go through power rule here. 2x, we go through power rule. 2x becomes 2x squared over 2. 3 becomes 3x. And then we have a plus c. Clean this up. 2's cancel out. We get x squared plus 3x plus c. We have a specific order pair that can allow us to move from a general form to a specific form. Plug 1 in for x, plug 2 in for y, and then we solve for c. So 1 plus 3 is 4. We subtract 4 from both sides. We get negative 2. So our c value is negative 2. Our function is x squared plus 3x minus 2. Okay, so here's number 20. We have a piecewise function. Which of the following statements are true about the function f? Just to get a picture of our piecewise function here, I have x plus 2 up until x equals 3, and then to the right of 3 I have a graph that has a positive slope of 4. So which of the following is true? Now if I have the graph in front of me, we can see that a function is continuous if there are no breaks. So at x equals 3, we see that these two piecewise functions connect at the same y value. They both connect at a y value of 5. So the graph will be continuous because these two branches connect at the same y value. Now to be differentiable, however, means that at this point, these two piecewise functions must share the same slope, and we see that's not the case. Up until 3, there's a line that has a slope of 1. And then to the right of 3, we see that this has a slope of 4, right, mx plus b. So if there is a sudden shift in slope, no longer differentiable, it's a sharp turn. So we can also use the derivative to kind of show that as well. If I find the derivative of both these functions here, the slope, the derivative x plus 2 is 1, the derivative of 4x minus 7 is 4. So we see that these don't agree. There's a sudden change in steepness from slope 1 to slope 4, so because of that, our function is not differentiable. We can also say the limit as x approaches 3 from the left and from the right of f prime are not equal, so our function is not differentiable. If the graph is continuous, the limit has to exist, so option 1 is also true. Okay, number 21. Second derivative function is shown to us in this graph. And we have f double prime that's given in terms of a and b. The graph of f double prime is shown. Where does the graph have a point of inflection? So point of inflection is going to be where f double prime changes signs. So we see that to the left of A, this is part of concave up. Part of the graph is showing concave up because it's above the x-axis. Below the x-axis represents concave down. Only if the graph actually crosses over the x-axis is there a point of inflection. So we see at point A, it crosses from positive to negative, so that's a point of inflection. At 0, it crosses from negative to positive. Now at B, even though f double prime is 0, there is no change in sign, so there is no point of inflection. There's no change in concavity. So only at point A and at point 0.